Hi, ladies and gentlemen. Today in this video we're going to discuss the different types of nuclear decay and kind of understand why they are important and why they're worth studying. So our goal for today is to learn to determine the outcome of a nuclear reaction. And in order to do that, we need to discuss the different types of nuclear decay and the way they affect the identity of the element. Now, essentially, this is what nuclear decay is. This is an example of nuclear decay on the screen. In this case, we have two hydrogen atoms that come together to produce something new. Okay? And during that process, energy is released. Okay? In this particular case, in the form of a neutrino and a neutron. But here's the tricky part, or here's the part that's most relevant. Nuclear decay, one type of nuclear decay, is when two elements come together and they form something completely new. In this case, I'm taking two hydrogens and turning them into helium-3. Okay? Now, that particular reaction, is called nuclear fusion. So, we're going to talk about several types, including nuclear fusion, but here's the gist of a nuclear decay. Atoms with too much energy are radioactive. And what happens is they get rid of that energy through nuclear decay. Okay, and there are different types of nuclear decay based on the identity of the element and its particular type of energy. But basically, atoms with too much energy get rid of that energy through nuclear decay. Okay? Now, here's a particular type of nuclear decay. You will notice that we go from uranium to thorium. So, when it comes to nuclear decay, there is a change in the identity of the element. Okay. Now, we get something new. So like I said, we start with uranium in this case, and we end up with thorium and helium. So this particular type of reaction is called alpha decay, and we'll talk about that in a moment. But I want you to notice there is a change in the atomic number. So when it comes to nuclear decay, there is a change in the atomic number. Often referred to as Z. However, I want you to notice that the atomic numbers of the two what are called daughter nuclei still add up to 92. So there's no loss in the number of protons. It's just they kind of change a little bit. Okay? And that's going to be particularly important. There's no loss in the number of protons. Now, there is also a change in the atomic mass. So there's a change in mass. In this case, we're going from uranium-238 to thorium-234. However, just like with the atomic number, the combined masses still add up to what we started with. Okay? There's no massive loss in mass. There is a tiny, just for clarification, there is a tiny loss in mass as some mass is converted to energy, but that is beyond the scope of this particular lecture. Okay, now let's go ahead and talk about the different types of nuclear decay. In this case, okay, this is another type of nuclear decay. We're going from thorium-234 to radium-230. This is called alpha decay. Oh, it would help if I spelled it correctly. Okay? And what alpha decay is there is a split in the atom to a smaller atom and what is called an alpha particle. Okay. So in this case, I have thorium, which turns into radium-230 and produces what is called an alpha particle. Now, an alpha particle also looks like a helium atom. Okay. However, in addition, I want to draw your attention to the fact that our mass numbers of the alpha particle and our daughter nuclei add up to 234. Which is what we started with. Okay? It is normal and expected that in a nuclear reaction, the mass numbers on one side add up to the mass numbers on the other side. The same is true of the atomic numbers. We start with 92 as our atomic number, and we end with 92 as our atomic number. So when we predict these later, we have to remember that the atomic number on one side balances to the atomic number on the other side. Now, once again, this particular type of reaction is called an alpha particle, or alpha decay, which looks like a helium atom, and they're typically charged. But once again, that's beyond the scope of this particular lecture. So this is a type of nuclear decay. Another type of nuclear decay is called a beta particle. Okay? So this is called beta emission. We still have all the hallmarks of a nuclear decay. In this case, the identity of the element goes from phosphorus to sulfur. Our atomic numbers still add up to the same, our atomic masses still add up to each other. They still balance, okay, to 32. This is my beta particle. Sometimes it is represented by a symbol that looks like that, just so you know. That's the Greek letter for a capital beta. Maybe lowercase. I don't remember. I think it's lowercase beta. Yes. So one thing I want to draw your attention to is one thing that makes us different is our atomic number, in this case, is 15. But here is the change in atomic number. The atomic number actually goes up. The atomic number increases by 1. So they still, however, add up to 15. this is where it gets confusing. A beta particle has a negative mass because what's happening is a neutron is turning into a proton. So with beta emission, I'm going to run out of room there, so I'm going to drag that now. With beta emission, a proton, I'm sorry, I lied. A neutron turns into a proton. Okay? And during this process, energy is released. Now here is another type of nuclear decay, and this is called positron emission. Okay. Positron emission looks similar to beta particle emission. And the reason for that is because it's a proton turning into a neutron. So it's kind of like the opposite of beta emission. In this case, the mass numbers still add up to the same on both sides. The atomic numbers add up to the same on both sides. However, the identity of the element changes. In this case, we're going from iron to manganese. So, in positron emission, a proton becomes a neutron. And since we're talking about something with a mass of 1 turning into something with a mass of 1, there's no change overall in the mass. Now here's a type of nuclear decay with which we're probably familiar simply from the media. Okay? In this case, we have fission. In fission, a large nucleus splits into 2 or more smaller nuclei. Two or more smaller nuclei. However, we still obey all of our rules. Okay? In this case, the identity of the element goes from uranium to xenon and strontium. So we're still changing the identity of the element. However, we're splitting this very large element into a smaller element. Now, what I'd like to draw your attention to is this neutron right here. What happens is we have this very large uranium, 233. Okay? We take this little neutron and we bombard that atom, and it actually splits into 2 smaller elements, plus 3 little neutrons. Okay? That's what fission is. And those little neutrons go on to bombard other larger nuclei. Okay? However, our mass numbers still add up. In this case, on one side, they add up to 234. On the other side, they add up to 234 as well. But what I'd like to draw your attention to is this 3 right there. That means that I have 3 neutrons. Okay? That 3 is called a coefficient, and it means that I have 3 of whatever comes after it. So 137 plus 294 comes up to 230, plus these, or 233, sorry, wait, 230, yes, comes up to 231, I'm sorry, 231, okay? And when it's added to those 3 neutrons, we get 233. So you'll notice our mass numbers still balance on both sides. Our atomic numbers, on one side, it starts with 92, and remember, neutrons don't have an atomic number. So it starts with 92. Give me a second to move this down. Oh my goodness, I moved the wrong thing. Okay, I can't move it right now, so we're not going to move it right now. Okay, so on one side, they add up to 92. On the other side, they also add up to 92. Okay, 54 plus 38 is 92. So our masses still balance, our atomic number still balances. And this is an example of fission. Now, when you have to predict fission, in class at least, you will know the identity of one of the daughter nuclei, because that's how you figure out the other nuclei. In reality, in the lab, they do the same thing. They kind of identify it by atomic number and properties, and charge and things like that. Now, the last type of nuclear decay that we're going to talk about is called fusion. And this is the one that we're going to talk about a lot with stars, okay? Because this is a very, very high energy process. Produces lots of energy. So this is the primary driving force behind stars. So this is called fusion. And this happens when smaller nuclei combine into larger nuclei. Okay. So fusion is when smaller nuclei combine into a larger nucleus. Not a nuclei, I'm sorry. Let's be grammatically correct, Dr. Clark. However, all of our rules still apply. Our mass numbers on one side add up to our mass number on the other side. Our atomic numbers add up on one side to whatever it adds up to on the other side. And you will notice that the identity of the element has changed. We start with more, we start with a larger number of nuclei, and we end with a smaller number of nuclei. In this particular case, 2 hydrogens are coming together to form a helium, and this is part of what's called the proton-proton chain in stars. This is the primary driving force in what gives stars such a high release of energy, because nuclear decay ultimately is a release of energy from unstable nuclei. Okay? And this is just another type of nuclear decay. So that's all our types of nuclear decay that we are going to cover, because they are the most basic types of nuclear decay. There are other types, like electron capture, neutron capture, proton capture, some other bizarre types. with which we do not need to be familiar because we are just talking about the basic types of nuclear decay that goes on in stars. Okay, so if you have any questions, feel free to leave a comment or feel free to email me, and I will talk to you all later.